Together, today's topic is how do machines see, and looking at the different things involved in computer vision.
Okay.
And this will be the roadmap. Like we'll just have the initial perspective of what the visual information processing is, then some understanding of how the visual information is processed in humans, and then the machine representation of these images and visual information, and how different computer vision tasks are achieved using this representation, and current challenges in computer vision, and some ethical and moral concerns which are related to. Then we'll have a question answer session. And say the visual system, or the visual information processing, or the eyesight is one of the most important senses, because it says like around 80% of what we perceive comes through our eyes, or its visual sense. So if you are blind, then you are losing a lot of real world experience. And let's see how the human visual system is. So brain has somewhat some spatial localization of functionalities, like it's the occipital lobe at the posterior side of the brain which take care of the vision, the processing of the visual information. And you can see like this is the top view of the cross section of a brain, and you see two eyeballs. And it's interesting like that, like the right visual field is processed at the left side of the brain, and left visual field is processed at the right side of the brain. So it's been seen like in cases where some lesion or damage happens to the this side of the brain, you lose half the vision. Like the if it's happening in the left, you lose the right visual field. Like you only see half the visual field. And human vision is uh, capable of color vision, depth sensing, detecting the movements, and it's been identified like there are different types of cells in the retina, or the which is uh, the receptive part of the eye. Like there is a flexible lens which can focus light and create image on this retina part, and which is being then converted to the neuronal signals and transmitted to the brain. And this retina has majorly two types of cells. One is called rod cells, and other is called cone cells. Rod cells helps in uh, low light vision, and low light and monochromatic vision. And rod cells have three different flavors: one for red, and one for green, and one for blue light perception. And it helps in color vision. And it's been known that the infants or neonatals won't have a fully developed visual system when they are born. Like it develops after the birth, and may take around 1 years of developmental phase. Initially, they can only detect the brightness changes and the movement of objects, and they can track the movement of objects. And it's the timeline of the visual system development in infants. Like around 4 months, they can focus on different objects and do perform some hand-eye coordination tasks, and they'll be able to identify or fixate their focus on faces. And around 6 months, the depth perception and color vision develops, and even color vision, like the blue color detection, develops later. And the 9 months, they can do precision grasping and interaction with the objects. And around 12 months, around after 1 year, they can detect objects clearly. And these are two quotes from two different peoples. The Helmholtz was a physicist, German physicist, and he says like the perception is our best guess as to what is in the world given our current sensory input and our prior experience. So he pinpoints the importance of prior experience or the training part which is required for proper uh, visual system development. And Oliver Sacks was a well-known neuroscientist, and he says like every act of perception is to some degree of act of creation, and every act of memory is some degree of an act of imagination. So it throws some light on how the neuronal processes are, like the every act of perception is different. Like even if it's just the taking in the light and doing some processing, like for humans, it's some changes also happens with every perception. And let's jump to the machine representation of visual information, how the machines are dealing with visual information. So consider this. So am I audible and
Yes.
yeah. So consider this thought experiment. Like there is Alice from Alice in Wonderland, and you have Bob Marley. Say they were classmates in a school, and the teacher has given some homework to draw some house and tree and some scenery. And Alice, as usual, went to the Wonderland and uh, end up eating some eat me cookie. So it made her only able to say yes or no, nothing else. So this is the situation, and she has figured out like there is a old telephone with which she has called her friend Bob, and she has drawn her. I mean, she has completed her homework, and now it's like she know like she won't be able to get out of this wonderland. Anytime sooner. So she wanted this uh, homework to be submitted as a school. So she wanted this to be exactly reproduced by Bob. So only thing she can say is yes or no. So how do this information, this visual information, be coded and transferred to the other end, just with yes or no questions? Anyone?
Uh,
Hello.
Bob will has to like kind of initiate the conversation, but he won't know what actually is happening. So like it'll
Okay.
be quiet.
So let me extrapolate this situation. Like this has been already happened, and they have come up with some communication protocol.
I mean, Bob can keep on asking questions, and then whenever it hits the mark, Alice can say yes. Probably.
Yeah, it's some way it's right. Like consider like let this image be drawn on a graph paper. So graph paper, each of there are n number of cells which are arranged as rows and columns, and each cell can be 0 or 1. So Bob can ask like the is the cell at 00 black? If it's no, he can mark like he won't be marking in his graph paper and say here the uh, 1 5 cell is black. When Bob asks like is the cell at 1 5 black, then Harry says yes, and Bob can also mark the cell as black.
Mhm.
Uh, uh, so this way, like this is an example of a binary image where each cell can hold a value of 0 or 1, either black or white. And this way, some visual information can be coded and stored, transmitted, and reproduced. So this is the basic image representation in a computer. And there is a theoretical backing for this coding theory, which is known as the source coding theorem by Shannon. And it says like how many bits are required to code an information. Say like there are you want to represent 255 gray shades, 256 gray shades like 0 to 255 values. Then you need 8 bits. So 2 raised to 8 is 256, and you can represent uh, 256 gray shades. So this gives some idea about the theoretical limit of representing a coded information using bits. And now see like how this real world visual information is converted to image file formats. So in digital camera, there is just like eye, there is a lens. In eye, what happens for focusing the lens curvature changes using the muscle contraction, and here in the digital camera, it's like the forward and backward movement of the lens itself. And there is an image sensor just like the retina in the eye, and for the color image sensors there are three types of image pixels, like say one for red, green, and blue, arranged in this mostly in this fashion. Like, and the green uh, image sensors will be twice the number of twice the number of than the red and blue. And this particular arrangement has some name, like it's called Bayer pattern. And so each of these image sensors are having um, has their own image, the color filters. The red one only let the red light to pass, and the green one only let the green pass, and same for the blue. And once it hits this the sensor part, the either it's a CCD or a CMOS sensor, then it creates some charge which is directly proportional to the intensity of the light it has been hit. So it basically it converts the light intensity to the corresponding uh, amount of charge. So this shows the end-to-end processing which is happening in a digital camera. Like there is an image and lens. Lens focuses this image uh, on the sensor, and it has this mosaic filter which has this RGB color filters, and then there is this image sensor array. And image sensor array, in image sensor array, when the lights hit, it produces the charges at corresponding positions, and it's being read and passed through an analog electronics for amplification, and then it's been converted to digital formats like the numbers, as you like the for say consider like you are using some image format which represents 256 shades of intensity. Then it's been each of these uh, voltage information from each of these cells will be converted to any number between 0 and 255 based on its intensity level. And there will be some digital image processing part where uh, the camera does some post processing like the white balancing or some other custom settings which has been set on the camera. And then there is a image buffer where this previously processed image cell, the pixels will be stored, and once it's complete, it will be transferred to the storage. That's how the image processing happens in a digital camera. And usually there are multiple file formats. One is the raw image, which will be directly taken from this sensor array output, like just after this amplification and ISO setting, like the ISO setting changes the amplification of this each of these signals and do some AD conversion. So it's a digital number for each of these pixels, but it may not be like 8-bit, like it may be 12-bit or 14-bit, like which carries lot many sh shade information. And for the JPEG formatting pipeline, it will be the, I mean, there will be this layer interpolation which identifies, like we have seen in the pair mosaic pattern, where the red image red filter is there. There is no information coming which gives what is the green and blue value for that particular position. So that needs to be computed from the information present in the uh, uh, this particular red pixel and the information around the that pixel. So that needs to be generated, and then each pixel will have red, green, and blue values, and then some white balance, contrast, saturation, sharpness, all those post processing comes, and then the compression algorithm which compresses this information to uh, this 8-bit format, JPEG format, then you get a JPEG file. So these are the two major types of processing pipelines and the end results. And the image file somewhat look like this. So this is a grayscale image which only contain the shades of gray, and this red portion is being magnified here, and you can see like the this three values like 78, 171, and 82. Like it's a number between 0 and 255, each representing a value corresponding to the grayness of that area. Like the 171 is more towards white, and 78 is somewhat towards the black side. And the on the rightmost side is the um, hex, what you see in a hex editor. Like if you open the file in a hex editor, you can see the hexadecimal values of this information, like 4E is 78 and AB is 171 and 52 is 52 in hexadecimal is 82 in decimal format. So this is what the actually the computer see. Computer see only the numbers and the positions where these numbers are. The same similar representation is in the given for this below image also. And any questions, any comments, suggestions so far? So we got the numbers, and then comes the computer vision part where we do the processing and do these to deal with certain tasks. And the computer vision is seen as a multidisciplinary field, like it has uh, different uh, disciplines interacting, like the neurobiology we have seen, like the most of the things are inspired from the human brain and how the visual information processing is happening in humans. And physics, there is optics part, like the lens is uh, uh, things to deal with light is there. Then the physics is obviously there. Then the cameras imaging part and the signal processing part, control robotics, like if it's a robotic machinery which is using this computer vision and the artificial intelligence part and machine learning, when you are uh, using these images to learn something and create models and use that models to do some inference later, and obviously the mathematics. And there are image processing, machine vision, computer vision, all has some intersection as well. Machine vision is when machine vision is a discipline, the system engineering discipline, I would say. Like it involves the image capturing part, the machinery is involved, and the processing and the application and the actuators, all those things. If at the system implementation level, and the computer vision, that is purely the computer science part where the image processing is happening. And image processing is a, I mean, just the if you're just dealing with manipulating the images and all. And majorly, previously it was like the people were not using any machine learning or deep learning. The people were dealing with the images just like they are matrices or arrays of numbers. So you do some transformation or you do some pattern recognition uh, manually, like the through if else routines or if else condition checks and all, you will detect something and all. Then came this idea of machine learning, where you can use this data and learn from it and then create some model and do some tasks. Like say, consider like you have an image and you want to detect whether there is a car or not. And in previously in machine learning systems, what we do is like the someone has to, some expert has to define what are the features to be extracted, whether I look for a color, whether I look for the shape, whether I look for the texture. And when these features are identified and you write some code to extract these features and convert it to vector or numbers, then you create a classifier and train that classifier, and then you have an inference stage where this trained model will be used to classify the new images which are coming. Like the new images, from new images the same features will be extracted and fed to the pre-trained model, and you get the output, like whether it's a car or not. And then came the deep learning era, like in which like the feature extraction part is also part of the learning process. You don't manually curate the features. Instead, the uh, the deep learning system itself learns what all features needs to be extracted. It will be fed the raw pixels, and after training it will also train its feature extraction part. And major change in the computer vision happened when this ImageNet challenge came. It's well known as the ImageNet moment in computer vision. It triggered the this deep learning boom in the industry. And previously, this research were mostly focused on academic things, and there were only very less number of industrial applications or real world applications. And the Dr. Feifei Li, she has created some ImageNet, the challenge known as ImageNet challenge. She has curated a data which is directly connected to the this word net which we have seen in the previous lecture, like the different word groups or synsets representing uh, some concepts, and for each synset there has been n number of images curated and annotated. And there is this ImageNet challenge where the data is there and you have a submission deadlines, and all people from different universities or different groups compete in that and submit the results and then publish papers and all. And you have seen this was kind of an image classification challenge, and you in the right hand side you have seen like how the accuracy of these submissions to this challenge has reduced. Like when it started, like it was the accuracy was somewhat around uh, 25. I mean the error rate was around 25% of the means 25 images out of 100 were classified wrong. And then around 2012 it's like 15, and when it uh, happened in 2015 it's like 95 percentage accuracy, like only 5 percentage error rate. So that with that accuracy the people tend to notice like this can be used in real world applications, like the computer vision can do tasks as good as humans can. And the major interesting thing which triggered this revolution is this convolutional neural network architectures. So you can I can show you a external 3D visualization of a convolutional neural network. So the convolutional neural networks are arranged as. Can you all see this view?
Yes.
Arranged as layers. Like there'll be an input layer. Input layer will be directly connected to the pixels of the image, and there'll be a number of layers which are arranged in a hierarchical manner. And this particular thing is for identifying numbers between 0 and 9. Like if I draw something here, like I draw 3 here, and it forms I mean, it's a pre-trained network, and you can see visualize the how each layer is working. Like the bottommost is the input layer where this pixel information from this drawing has been directly taken, and above that there is 1, 2, 3, 6 next layer, like the first level layers, and each of these the individual blocks in each of these layers is known as neurons in this case, and each neuron has a receptive field, like you can see some lines being connected from this particular node to the layer underneath. Those are the information which are taken by that particular node in this layer from the previous layer. So each of these layers are connected like this. And at the end, it's been tapering towards this. It's been detecting some uh, higher level features. At the first level, it was looking at the pixels. The next layer, it may be looking at the some particular edges, and then when it goes up in the hierarchy, it looks for higher level features. And at the top, there is a classifier which classifies this extracted features to corresponding uh, class. Like this is 3, and the neuron corresponding to the 3 has been lit up. So let's try another the same way 2 has been lit up. So this is how the convolutional neural network is operating, and there is this name. The convolutional neural network comes from the operation called convolution. and this is what happening in each of these neurons. Like it's like uh, some way it's like adding up and taking average. There will be a x by x window for each of these, like the which is shown by this receptive field. Like say, if it's 3 by 3, the 9 pixels from 9 neural information from the previous layer will be taken and I mean multiplied with this filter and then taken and updated.
Suppose I have a doubt, this one, how, I mean, I missed the first part where some bit of the brain thing was talking, you were talking. So, how is this connected to the vision thing?
Like this is like some way like say human brain want to say like I can see like directly say that this is a two.
Yeah.
So how
How
do
machines perceive too?
machine does this process?
Okay, this is the way the what do you call the visual perception has been coded in the machine world.
Yeah, this is one approach of doing the image classification task, like detecting what is that image.
Uh-huh. Okay. Okay.
Uh, Image classification happening in um, machines.
Subhash,
Yeah.
so I have a question for this thing. So if a person is having a blurred vision, and say for example, if it's not only number, but it's something that he has seen before, like he has a what I would say, an image of that particular object or maybe that particular sentence, anything. So that AI, with the help of AI also, it can be tracked if they have like blurred vision or something like, or through the machine also.
I couldn't clearly get that question. Like the human has this person is experiencing some blurred vision, like say he's having short sight, or then he's seeing the objects at longer distance as blurred objects, and
So is this so if the person is having this kind of behavior, like they are not able to see things properly or like the blurred vision. So if the same thing, like for the AI also, if there is anything blurred or if there is like not properly shown, that then the AI can track that thing, like whether it's letter or maybe that particular sentence or maybe that particular person, anything.
like say due to some image capturing issue, the image at the input level is blurred. Are you talking about that?
Yes. Yes.
And it depends on how this machine has been trained, and it always gives some results, but confidence level of that result may differ. Like, say in this case, you are with the 90% confidence saying like this is two. This machine is saying like that. Then if it's a blurred image or something, it may say like it's 30% with 30% um, confidence. It's a one with 40% confidence. Is a two. Multiple options will be there.
Okay. Okay. Thanks.
Okay, then let's get back to you here, and uh, you can see how this being implemented, this kind of neural network being implemented in code. You can see at this part, like uh, there are ways to add layers. Like input layer is 150 by 150 with three channels RGB, and you are added a convolutional 2D layer with 16 filters. Like the second layer will be having the 16 different. Here it was 6, and uh, and each for I mean the filter width is like the receptive field is 9 neural information from the previous layer, and there is a processing called max pooling, which does what does it? do is like it has like this 2x2 window. From each of this 2x2 window will be moved along this previous say like the whatever is processed in the using the filters like the out of this four elements whatever is maximum will only be transferred to the next layer. So it's kind of a dimensionality reduction happening, and then again there is another 2D convolution layer, then again max pooling, 2D convolution and max pooling, and then the whole thing has been flattened like a linear array, and then there is a hello.
Yeah, your voice got cut off in the middle.
Hello. Yeah,
Ah,
call got dropped in between. This is how the that particular I mean the uh, convolutional neural network be implemented using this Keras library and TensorFlow. And let's get back here. And now comes the application subtasks in computer vision. There are many more uh, subtasks and applications than added here. But let's see the major subtasks. Like one is the face recognition. Then you have the image retriever, like in Google image search and all. You can search similar images, and anomaly detection, like if someone is running, some crowd gathering is happening. Those kind of anomalies can be detected. Then the style transfer, where you can create artistic images using styles transfer, like if you train using uh, paintings of a particular painter, and you can generate the same style paintings given an real image and this learned network. And image captioning, like it's like the captioning the image, like giving the description of that image. And emotion recognition and image in painting, where the missing parts of the image are in painted automatically. And the semantic segmentation, like you can detect say chairs, a bed, or different objects, and say all like the all can be represented, similar things can be represented with annotated with the same color and all. Like the car, it's helpful in this self-driving cars and all, where it can detect all the cars, it can detect the pedestrian, and it can semantically segment those image frames. And object detection and tracking can generate new images given the training set of a large number of images. And pose estimation, image super resolution, like the you can generate high resolution pictures from low resolution images. And the self driving cars, of course, like making the driving decisions based on the image frames. And action recognition, and if image to image translation, like the you have a image, like here it's say a nighttime image, you can convert to daytime image, you can convert a real geological map to a uh, I mean this kind of map. And you can convert real life videos to anime type videos. And OCR, optical character recognition. So these are the major use cases in computer vision. So, to add to this, anyone can suggest where have you seen the computer vision applications in your life? Hello, anyone? Have you seen any of these applications in your real life anywhere?
report proctoring.
Yeah, of course, like the our remote proctoring tool, which does the object detection, uh, gaze detection, and the face recognition to some way, and face detection, post detection, and all. Any other examples?
I would say in Snapchat, it detects the face and then it automatically applies the filter. So that is one application, like using like whether the person is in the frame, like if the person is added in the frame, then the filters are applied to that. So similar to this, like
Yeah,
object identification.
yeah, like the most of the AR applications need this computer vision. Um,
Autonomous cars,
which one? Hello?
autonomous cars, auto-driven car.
Yeah.
Like they do the surrounding check and map what is where.
Yes, and some autonomous cars may use other sensors like LiDAR or uh, laser-based sensors as well,
Yeah, yeah.
along with this image.
Okay.
Like, can the image superscaling be used to fix a blurry image or not?
Yeah, that's the application for this image super resolution.
Oh, okay.
It can generate the that details which are not being present. It could have been pixelated if you zoom at level, but with this, it generates based on its the network generates this information based on its previous experience, training experience, and major. What are the challenges? And this is one thing which tells about the this current scenario of machine learning and all. Like the in media and all, it will be very much hyped and shown as the AI is going to take over the world in the recent years and all. But when you look at the some applications or some, I mean, from the experience of a ML developer and all, like it's like this is same as depicted here. Like the it's cat's been detected as a dog, and there are challenging problems like this. Like even for the humans, it will take some time to identify whether it's a chihuahua or blueberry muffin. Like the both each of these pictures have three black dots and the same color, similar texture, and also training and building such systems which can differentiate these subtle changes or fine grained details. That's another challenge. And now there's been someone as people have been demonstrating like how to fool these computer vision systems. Like this person is not detected as a person if he's hanging this colored image on his neck, and some random noise been added to this panda image, and it's been detected as gibbon by a well-trained network. For the humans, it's still panda. For the this trained network, it's gibbon. And other challenges are the for this deep learning system to work, it needs a massive amount of data, and the data curation part is a big challenge. And data annotation, like some problems needs this data to be annotated for semantic segmentation and all. Someone has to draw the outline of these objects and then mark it as say it's a car, it's a person, and all those things. And the amount of computational power it requires for this deep learning system to get trained, and the training time. Like if you don't have enough computation power, you have a large amount of data, your training time will increase. And another thing is major challenge is the non-explainability of most of these models. Like it has large number of parameters, and you don't. It's very difficult to find out like why this network has detected this particular image as uh, a cat, not as a dog. So that kind of explainability, like the is there an rule which has been learned by the system or not, or is it just looking at some texture, or is it just looking at some portion of the image and then doing the prediction? So that uh, I mean, adding that explainability in these models is one another challenge. And here I have given some training benchmarks, like for each of these models, how much time it took and what was the computation power used, and it's not visible, I guess. And now is the moral and ethical concerns related to this computation things. So the popular culture depicts this machine intelligence as I mean, which may turn evil and take over the human world, or I mean, start a war against humans. So popular culture has these themes always, like if the machine has given the power to, I mean, operate on its own, like the weapons being developed and it has a computer vision camera and it's been given, I mean, given the chance to fire on sight of a person or something, then it can cause damage to the person. And recently there's been news like some person being arrested based on a machine learning algorithm's prediction, like this person, I mean, face recognition algorithm gone wrong, and it's this person being arrested. So that's been in news, and then that triggered, I mean, uh, discussion on different levels, and Amazon suspended the police use of facial recognition technology, and IBM also dropped their facial recognition activities, and Google has released some guidelines on where they will use their AI technologies and all. So these are the recent events related to the ethical use of this AI and computer vision related systems. And that concludes our computer vision overview. And now questions. Anyone who wants to add to this, and any questions, suggestions, comments?
Yeah, not so recent. Like some time back in China, there was some like concentration camps. Like basically, the Muslims in China were being oppressed and all. And basically, like in that region, they had cameras installed almost everywhere, and that basically captured everyone's uh, like what they do and stuff like that, how they do. And the neural network basically predicted that if he's going to turn into a like a bad person, like will he murder someone and stuff like that. And the Chinese government are actually using that to imprison innocent people like Muslims and all, putting them into concentration camps just because like they're completely relying on that he did this thing, did like the way he lives his life, basically the daily life. And then they calculate that, predict that if they're gonna be good Samaritans or like may choose crime later on. So that's not a, I mean, yeah, that's one thing.
Yeah, that's been in news, and there's been a BBC documentary in which it's been depicted like the person who is entering the, I mean, entering the country from this airport, and when this photo is being taken, it's being that person can be tracked across multiple cameras and multiple places. And there are some systems like in even there was this Amazon car recognition and all, like they can also predict whether the person is a shoplifter or not based on their facial features and their appearance.
It's like next level prediction.
And the maybe the bias in the system is due to the such systems, like the black people will always be depicted as, I mean, the more associated with the crimes based on the how the bias the training data is.
Well, how would be computer vision used in this Samsung ka Neon, the artificial humans?
One thing is like there is an generation part where these human images are generated, and that might be trained using the actual human videos or 3D capturing of the humans. And if you want that to be in an augmented reality or something, then you need a computer vision processing to identify the things in the that particular vicinity and place this particular human on the ground.
Okay. And what about the robot assisted surgery?
Yeah, that also needs computer vision. Like it has to see, the robot has to see like what is there and then operate through it. This actuator and its image sensor. I mean the image information coordination, like just like the hand-eye coordination in humans.
Okay.
And in phones, you might have seen like the groups the photos based on the this faces. It does some face recognition and associate and groups automatically groups the images.
Mhm.
And even in image, and another thing is like in image search, you will see like this uh, based on your search query in language, it brings the images. And nowadays, this image captioning part is helping there. Like if its images are indexed uh, previously with all the image captions, like then instead of doing some meta information search, they can just do a caption search with the connected with this particular query.
Uh, so what can, like for example, there is image alt text, right? Which is basically for people with disabilities and all that. So can that be utilized into computer vision?
That old text usually needs to be manually coded in. I
Yeah.
don't think most of the times the people add that. It's been for one for this screen readers. Another application was for if uh, this uh, particular page been accessed through a command line or through a uh, text interface rather than a GUI. So those are the application for this alt text wala part. Then maybe this alt text can be automatically generated using this image captioning system.
Okay. Yeah.
And if it's properly, if you find some pages where this being properly done, like say it's Wikipedia or something is doing this properly, then you can curate the training data for this image captioning from these sites.
Okay. Yes. That's from my side.
Anyone else? Can we conclude this? Yeah, I have another call at 11, so let's conclude this and
Yeah.
we'll explore these computation subproblems in detail in upcoming sessions.
Yep.
So thank you so much all for attending this session and have a great day.
Thank you. Good day.
Okay. Thank you, Subhash.